What I'm going to do is give you this presentation we gave at the White House in April of 2016 and then again in December of 2016. We've been very thankful for the opportunity to help formulate national and global policy. And I'm going to go through some things very quickly here. So this presentation was given in 12 minutes. We were told that's all the time they had for us. We talked about the role of regrowing soil carbon to reduce atmospheric CO2. We presented a series of projects and what we've learned from those. We talked about data gaps, the technical needs to flesh out the rest of the science. And then we talked about a 1 million ton and a 1 gigaton demonstration project to actually take this to the land at scale, at a 100 million acre scale. And the first thing we formulated was a working hypothesis, and that was that carbon-rich soil is healthy. It's beneficial for the entire ecosystem, including us humans. So the economy that we celebrate benefits from healthy soil. Drawing down CO2 into the soil results in improved water infiltration, retention, biodiversity at all levels, reduced erosion, and contributes to livestock and rancher well-being and human health, not just the ranchers. A little bit of background. Right now we're emitting anthropogenic about 9 gigatons of CO2 and other greenhouse gases, CO2 equivalent, and releasing that to the atmosphere, and split between the land, the soil, and us, life like cattle and insects. About 2.6 gigatons goes into that sector, and about 2.3 goes into the oceans and other aquatic resources on the planet. And what's left annually excessive in the atmosphere is about 4 gigatons. So here's how the carbon stocks are distributed on the planet. Hopefully your blood sugar's doing okay here after lunch, and you can all see that there's different sized circles there. And those are scaled proportional to the amount of carbon in those sectors. So the oceans have, you can see, the largest quantity, but then the next largest quantity on the planet is found in soils. And we usually don't think of that. And by the way, the quantities in that brown circle are 60 to 70% depleted. That brown circle used to be, 1.7, 1.6 times larger. But we've lost that, and that's now up in the atmosphere, or it's been transferred into the ocean. So we speculated with Shell Oil Company, with their internal innovations group called the Shell Oil Game Changer Group. They worked with us for 3 years. They threw their best engineers at us, and we found only a few of their best engineers were really good at thinking differently about climate and thinking differently about ecosystems. But we took full advantage of those guys, and we said, you know what, there's 3.5 billion hectares of grasslands on the planet. And then there's another billion hectares of farmlands, croplands. So 3.5 plus 1 is 4.5 billion hectares of land where we actively manage the soil directly by cultivating it, by herbiciding it, by doing everything that you all know that we do, including using cattle as our agent to do things to the soil. And we said, what if we could improve the soil carbon level by 1%? And let me just give you some sense. The average amount of carbon on each acre of land here is about 100 tons. So a 1% improvement would be adding 1 additional ton per acre to a background of 100 tons. If you multiply, I'm not going to take you through the back of the envelope high-powered math we did here, but if you multiply one ton times 3.5 billion hectares, or by 4 billion hectares, it's 4 gigatons. So it's the exact equivalent, the bubble that went back, the excessive up in the sky, It's exactly the equivalent of what the annual excess is that we're leaving in the atmosphere. And what I'll show you is that we actually can improve soil carbon annually by as much as almost 3% annually, maybe 5% in the southeastern US. So is there something that's low cost and scalable with every farmer and every rancher who chooses to participate? It doesn't matter whether they give a crap about soil carbon or they give a crap about climate change. They benefit economically from improved yields, reduced costs, as the movie showed, to carry their herd, to care for their herd, steward their land. So this seemed, with the Shell Oil Company Game Changer Group, this seemed like a very promising alternative to look at. So I'll report on a handful of projects here. The first is a project that we started, we being Applied Ecological Services. We got a USDA grant, and we looked at a 30 million acre area called the Palouse agroecosystem. It's eastern Washington state up into Idaho and over into Oregon. And we eventually settled on a 7 million acre project area that was the most homogeneous with regard to mineralogy and geological history and a whole range of variables. And then we went out and sampled soil carbon on that landscape. And we developed a program. We now have 300,000 acres of farm land enrolled in what will become the first soil carbon transaction on the planet that's based on the measurement of improvements in soil carbon levels against a baseline. So we measured the baseline, and we'll be remeasuring, and the farmers are going to benefit financially. The farmers in the Palouse that we're working with are doing what we're calling low disturbance cropping. It's 1 pass no-till instead of 2 to 3 pass no-till, or conventional tillage, or even conservation tillage, which all have declining carbon stocks. And I won't take you through a lot of the details today. But the farmers are going to receive a revenue stream. The first tranche will be a $42 million transaction, probably the end of this year, early in 2018. 80% of the $42 million will go to the farmers. It's a brand new revenue stream that nobody has touched on the planet at this scale or from this source, just by improving measurably soil carbon. How did we sample a 7 million acre area, you might ask, and how did we do it cost effectively? Well, the way we did it was we stratified the landscape. We biophysically identified the areas that were similar with mapping. So the slopes, the aspects, soil, mineralogy, climate, precipitation, and Dave did a lot of this work at AES doing the GIS work. And then we went out and sampled soil carbon stocks randomly across landscape positions to understand the relationship between soil and this landscape. And we got the cost down to about 7 cents an acre to be able to do full meter deep soil sampling and soil organic carbon sampling. That's unheard of, but the reason we can do it so inexpensively is because every time we sample, this is too small to read, every time we sample an area, it's part of a strata defined by very specific biophysical and historical conditions. So if we know we've got that same strata over here and another place 10 miles away, they're identical with regard to biophysical conditions. So we don't have to learn about the differences. We've quantified the differences, and by sampling according to these strata, we can sample very efficiently. We learned that the top three, the top 3 variables that control everything on the landscape, especially soil carbon, is the precipitation, slope position, and slope aspect. So southwest versus northeast slopes, completely different vegetation performance. So those are some of the key strata. And then across the top in the blue ellipse, those are the soil treatments that we sampled. So we sampled farmers that have been doing this low disturbance cropping for less than 5 years, 5 to 10 years, 10 to 15, 15 to 20, 20 to 30. and then we compared that to the CRP fields and to the conventional tillage. And that gave us, over this large 7 million acre landscape, by sampling those treatments, we essentially sampled over 90% of the treatments that were being deployed on that 7 million acre landscape. So we statistically robustly covered it. Sampling, it's hard to see with the lights on, but there's randomly allocated sample points. We drove this ATV unit with a GPS out to the randomly allocated sampling points and pulled with a hydraulic ram, pulled a meter deep core sample, 2 inches in diameter, put caps on it, a barcode on it, and that went right to a lab. And it was sampled for bulk density by strata, and it was sampled for inorganic, organic, and total carbon, and some other constituents. And that became the basis for, you can see the conventional tillage, the different treatments, tillage treatments or planting treatments on the left. The soils lab analysis work that we had done is on the right. What we were able to measure on a 7 million acre landscape with R-square values, so accounting for the variance in the spread of the data, we accounted for the variance with greater than 50% accountancy, R-square values. And when we pulled out aberrant data points, we were able to get that up to about 65 to 70%. That's unheard of. Most soil sampling doesn't sample large landscapes. So this told us we were onto something. So what are the farmers going to get out of this? Well, the red line is the baseline, the regional baseline scenario. That's what's happening with conventional tillage and conservation tillage. And this is just a stylized graphic. What's happening is conventional tillage, every acre is losing about 2.02 tons of carbon per acre per year, and conservation tillage is losing about 1.73 tons per acre per year. So chisel plowing, which happens here every fall, and even conventional no-till was gaining carbon, but it was gaining it at a rate about 2/3 of what we're measuring with this one-pass no-till. Question?
That's because it's exposed to the air?
It's because they're turbating, they're breaking up the soil structure and mixing with air, so it's oxidizing and decomposing, like a compost pile. You turn it and it degenerates. So what's a typical, I won't bore you with the dollars, but a typical farm that's producing about 3 tons of carbon dioxide equivalent per hectare per year would be getting about $1.1 to $2 million over a 10-year period, which is not chump change, I'm told. I'm told it's pretty important. The other cool thing is they're able to reduce their tractor horsepower by about 90%. And that's just reducing huge amounts of petroleum use and emissions because of the improved tilth, the improved soil looseness, and because they're not doing tillage, they don't need 300 horsepower tractors. This is the enrollment poster. So I keep changing terms or figures, but this is tons of CO2 equivalent per hectare per year. So in the green area, the farmers would be averaging right around 5 to 7 tons of CO2 equivalent per hectare per year. In the drier yellow areas of Washington State, and this is about 9 million acres you're looking at, they'd be averaging between 1 and about 2.5. And at a value of about $10 to $13 a ton, a farmer in the green zone would be getting about $50, 5 times 10 per acre. I'm sorry, 5 times 10 per hectare per year. And if they have a 5,000 acre farm or a 10,000 acre farm, the numbers add up pretty quick. So the next thing I'll talk about is adaptive multi-paddock grazing. So with a wonderful research team, some of the characters you saw in the movie, the ranchers Neil Dennis and Gabe Brown that some of you have probably heard about, they're part of the ranches that we've been studying, but we're also studying ranchers that aren't as aggressive and innovative as those two guys are. so dumbed down versions of adaptive multi-paddock grazing. What we're learning in grasslands, and we've known this for a long time, is that the soil microbes mediate the system. And where we kill the soil microbes with anhydrous ammonia and fertilizers and other nasty things and not so nasty things, excessive manure loads, excessive irrigation loads, everything you put on the soil skews the microbial life in particular directions, and some of the materials kill most of the beneficial microbes. So we're learning without healthy microbial communities, the plants aren't mediated, and the nutritional value of the plant materials and the nutritional value and the quality of the food produced on the land isn't nearly comparable to what can be produced in a healthier soil system. So there's 4 ecosystem processes that we're working with: energy flow, water cycle, mineral cycle, and plant community dynamics. And all we're doing is changing the grazing systems. So this slide is the exact same location with a 10-year period of time between the time the first shot and the second shot was taken. And the only thing that changed was the grazing system. So there were no seeds added, no fertilizer added, no irrigation added. All that happened was they tripled the number of cattle on the land, and instead of leaving the land grazed continuously by the herd, they, like you saw in the movie, the cattle were moved in and moved out quickly. And the soil, the desert crust that built up in the image on the left was broken up, and the seed bank, viable seeds, tubers, rhizomes, turions, bulbs, came up out of the soil, and the image on the right is the exact same location.
How quickly is quickly?
Within a period of 3 years, there were noticeable improvements in soil water infiltration, and within a period of 5 years, the land was vegetated. And this was a 10-year photograph, I'm told, by Dr. Richard Teague.
They moved the cattle off, how soon?
Oh, the cattle like you saw in the movie,
Yeah.
the cattle were moved in for 1 to 2 days,
Okay.
and then moved to the next paddock, and 1 to 2 days and moved to the next paddock.
Oh, you need a lot of paddocks.
On this is like a 20,000 acre ranch in northern Mexico, where they get 9.5 inches of rain, 10 inches of rain a year. And this was Sonoran Desert. You know, this was, people threw their hands up and said, we can't do anything with this. Well, here's an interesting study by Richard Teague from Texas A&M, who's part of the research team. He put GPS collars on cattle. And what this shows is every green dot shows where the cattle were using the land. And what you see is they used a very small percentage of the large ranch. And what he learned was that overgrazing has nothing to do with the number of animals. It has to do with the time that the animals are in contact with the plants. And if the animals are in contact with the plants consistently, day in and day out, like you saw in the movie and heard the movie, it weakens the plants that are the durable plants, the long-lived plants, and it selects for and favors weedier plants that are short-lived, don't have deep roots. I like his saying, 1 cow grazing on 10 acres all season can kill thousands of plants, but 1,000 cows grazing the same acre for 1 day will not kill a single plant. Wow. So that's not science-based. That's just a catchy way to state what he's learned. So overgrazing is a real problem, but it's a problem with how long you leave the cattle in the property. So what they did here is it's the exact same ranch, and they broke the ranch up into small paddocks and put watering points where the cattle could water, distributed those, and then they moved the cattle around, and they improved the efficiency of grazing using Richard Teague's measures, but they also measured all sorts of improvements. They measured in northern Texas there 3 tons of new carbon added per hectare per year under the SAMP grazing, adaptive multi-paddock grazing, compared to the continuous grazing. decrease the bare soil, soil structure, improve soil fertility, microbial composition, water holding capacity, plant productivity, plant species composition, and livestock production all increased. I won't bore you with this. This just shows that the high continuous grazing, there's high levels of surface water runoff, and groundwater flow is lowest. And as you go over to AMP grazing, basically the exact opposite. AMP on the far right, you know, the groundwater infiltration rate and the flow into the ground increases significantly, and the surface runoff decreases significantly. The EX is an exclosure that was a native prairie. So a native grassland that hadn't been grazed. Isn't that nice to see the AMP grazing is driving the system back toward a reference natural area? That's a reassuring little discovery. So the next thing I'll do is take you to Alberta. We started a study that we'll now be doing for the next 5 years to understand whether this grazing relationship with soil and water occurs in Canada. I don't know why it wouldn't, but you know, they talk differently up there and everything. So we wanted to test it. So we went to the 4 main ecoregions in Alberta, shown with the stars. You can see there we did the same stratification, biophysical stratification process, and then we chose AMP farmers, AMP ranchers, and conventional neighbors right across the fence doing continuous grazing. Went out and stratified, we stratified, and then we did pre-sampling to understand the variability, which we used to understand the sample sizes we needed to statistically do the sampling. And then we went back and did the sampling with this hydraulic unit that, you know, extracts a sample. That's in the lower right. And then we also added automated infiltrometers, which are devices that measure water infiltration. And this blew me away. So this is like taking a pressure cooker, about the size of a pressure cooker, inverting it and plugging it into the ground, literally, with a water seal. And saturating, you turn the unit on, and it does a 100% saturation of the soil column, sometimes 10, 12, 15 feet. It saturates at 100%. And then you start running tests, and it applies constant head pressures, water depths of a certain, of a precise level, and it measures how much additional water and at what rate it can be driven into the ground. And so that's the infiltration unit. The other thing we did, and this is all shown in that other movie, The Luckiest Places on Earth. If you want to go to Vimeo and look up the movie, The Luckiest Place on Earth, you'll see this in detail. The other thing we did is we did carbon-13 isotope pulsing. Carbon-12 is what we normally breathe. About 99% of the atmosphere is the carbon-12 isotope. And we can, in a laboratory, remove the carbon-13 isotope molecules and concentrate that. And for $10,000, we bought a little canister about this big, full of carbon dioxide with the carbon-13 isotope. And these tents were built, and little tubes you see going to those tents, and we pulsed the vegetation, so we pulsed all the life with this carbon-13 isotope. And then we were able to follow how that carbon-13 was taken up by the plants in the photosynthetic process, and we could follow the carbon-13 down into the root zone and how the microbes distributed that carbon-13. We could, if there was outgassing of methane or carbon dioxide from the soil, we were measuring that in real time 24/7, and we were able to understand the fate of this carbon-13. So very interesting, really high-tech and expensive stuff to do. Basically what we learned was the AMP grazing, the soil organic carbon accrual rates were about 1.4 to 2.4 tons of carbon per hectare per year higher in the AMP grazed compared to the across the fence continuous grazed. And it was lowest in the sandy soil and highest in the clay loam soil. This blew me away. the infiltration rates, and by the way, this is a soil profile taken 10 years after the farmer or the rancher switched to amp grazing. So you're looking at about a meter in soil depth from the top. Literally, there's a fence line between these two. And they have the same grazing history. Two brothers that own these farms. One brother said, I'm not going to bother changing. I'm going to continue running my land into the ground. The other neighbor changed. Hopefully you can see the color differences. That's in a 10-year period. But the infiltration rates blew me away. In a sandy loam soil, which has incredibly high infiltration rates, we were statistically measuring an additional centimeter per hour of infiltration, even in the sandiest, highest infiltration soils. And then in heavy clay loam soils, we were measuring almost a 9 or 10 inch improvement in a period of 10 years. That's remarkable. If you multiply that infiltration rate times 7 million acres of land, or 1 million acres of land, whatever you choose, it's huge volumes of water that are going into the ground rather than running off the surface of the ground. The other thing we learned is that native plants and cultivated plants they behave completely differently with regard, and we've known this for years, but now we've got real data, with regard to soil carbon. So on one ranch, the Towers Ranch, everything they have is European brome grass and tall fescue, introduced shallow-rooted cool season grasses. What we found there, so you're looking, this is a meter deep, and you're looking at the soil carbon levels in the adaptive multi-paddock grazed, the high density continuous, and then the difference between the two is the black line. What we learned was that the cool season non-native grasses put their carbon in the upper 10, 15 centimeters, and they really don't drive carbon down deep. And the native grasses very quickly saturate at the surface and then start driving soil carbon deep. And we found in some native grass stands, instead of 100, I'll just give you a reference point, instead of 100 tons of carbon per acre, we're finding 300 to 500 tons of carbon per acre. So just off the charts. So if we convert ranch land to a mix of native cool season grass and warm season grass, we can confidently drive a huge amount of carbon into the ground. So right now, Dr. Teague is in Paris talking about the Paris Accord. Based on the data that we have, instead of the Paris Accord proposal for improving soils by about 0.4%, it looks like we can improve it annually about 1.1 to well over 2% instead of 0.04%, which is what's been negotiated in the Paris Accord. So I think, let me just do it. This is life cycle analysis. I won't bother you with that. What we've learned is that there's this aversion globally to a role for cattle and a role for livestock and actually becoming part of the climate solution. The IPCC said reduce livestock on the planet, reduce cattle on the planet by about 90%, and that'll take care of the methane problem. It's not true. And this is modeling results from a life cycle analysis that a group of us have published. I don't know if you can see it, but the emissions from all livestock, farms in green, emissions from farm soil erosion, and emissions from fertilizer manufacturing and crop production on the planet are all illustrated with these colors. If you reduce the ungulates, the ruminants on the planet, by about 50%, there's no significant change in the emission profile on the planet. If you start taking 25% of the ag land and 25% of the grazing land, and you convert that to this low disturbance cropping and to this amp grazing, there's a significant improvement, reduction in the emissions, and actually what's happening below the zero, the horizontal line, is rebuilding carbon stocks on the planet, rebuilding the sinks. If you could remove 50 and 100% or convert 50 to 100%, it does, the modeling suggests it does exactly what our back of the envelope prediction suggested, where we could take about 4 gigatons of the excessive atmospheric emissions annually and put it back into the soil at a very low cost. And I think there's too many other things here. Just to summarize, we're confident with the data that we have, and this whole program is now expanding throughout the northern Great Plains, the southeastern US, and across 3 provinces in Canada to build bigger data sets to inform policy. We're confident with the data that we have that, the hypothesis of, more soil carbon leading to water resilience, reduced erosion, improved biodiversity, food quality and health, and improved farm economics, that it is real. And it's vitally important to think at these scales and operate at these scales if we're going to solve big problems. These were the data gaps we talked about, and this was the 1 million metric ton project and the 1 gigaton project that I won't bore you with. And here's the summary we did for the White House. And there were a couple of other slides that we shared. People are fixated on trees, old growth trees, as being long, durable storage organs for carbon. And what we've shown with the series of studies here, that the carbon in the soil, for example, the carbon in the soil in the upper Midwest, the red circle you see there, Wisconsin glacial till plain, most of the soil carbon age in the upper tenth of a meter is 100 to 200 years of age. That's the average age of the soil carbon. You go down you go down 1 to 2 decimeters, and it's 1,500 years to 12,000 years of age. The average age is within that range. You go deeper than a meter, or deeper than 2 meters, and it's usually about 12,000 years. The place we're working in the Palouse, or in arid New Mexico, again, 100 to 200 years of age in the upper tenth of a meter, down to 2/10 of a meter. The soil carbon average age is about 30,000 years of age. 2/10 of a meter to 5/10 of a meter down, it's 3 to 5 million years of age, the average age. So we've been fixated on trees. In fact, the longest lived carbon stocks on the planet are in the soils. And even longer lived stocks are fossilized in the form of limestone. So this became a really important conversation with the policymakers who are so concerned about, they want to make a decision and make sure everything is going to last forever, which nature doesn't last forever, but that's a human construct. So I think with that, there's a really cool paper, if you're interested in this subject area, there's a paper, a 2013 paper that really brings together archaeological evidence, evolutionary evidence, and climate evidence that shows that when the Earth historically had, I don't remember what it was, 2,500, 1,200 to 2,000 parts per million of CO2. At that time, ungulates, grassland specialists evolved, and grasses evolved that could tolerate the grazing pressure. They didn't have their growing apices above ground, they were below ground, like the grasses we have now. And mollisol soils, our deep black soils, evolved at that time. And with the evolution of that system, the carbon levels on the planet went from about 1,400 to 2,000 parts per million to about 260 parts per million in about 2 million years. So we now have these grasses, we have these soils, we have these microbes, and we have these grazing animals. We don't have to wait for the evolutionary process to occur, so this can all happen a lot faster. So the Earth is telling us, hey, we've done this before and, learn from the lessons that this planet has experienced. So this is additional reassurance that the science is on track with a possible solution that will be the most cost-effective and scalable
How do you
strategy.
access this paper?
Excuse me?
How do I find it?
I'm sorry, look up Retallack. Let me go back, Neil. Retallack, 2013, Global Cooling by Grassland Soils. Just look that up and it'll come right up.
Thank you.
University of Washington. This is one of the best papers I have ever seen that brings all this uncertainty together with just so much content. It's a remarkable paper. So I think with that, I'll shut up. If there's any, here's the global distribution of pastures, grazed grasslands. Here's the global distribution of croplands. I have the soil carbon mapping for the whole world, but I apparently won't come up.